All right, so we're talking about Thevenin and Norton here, and I forgot to mention that this voltage source is called the Thevenin voltage. This resistor is called the Thevenin resistance. It's this current source is called the Norton current, and then this resistor is called the Norton resistance. Okay, not super crazy stuff, but now we're going to get into the general process, which does seem a little bit daunting. I only have words on this slide, so I don't have a whole lot of room to write. Hopefully I can just talk through it, and then we can just go right into solving an example. Basically, the Thevenin and Norton general process here, I'll just draw a little circuit here. So let's say I had a circuit, and I have some interesting things going on in my circuit, and then I have my load resistor connected right here. I'm going to draw it in red. Okay, and so again, Thevenin and Norton is meant to take, it's basically meant to analyze what is the voltage and the current through my load, given that I keep changing my load out. So what we do is we're not interested in the load resistor for the equivalent, so we take it out of the circuit. That's the first step here. Is remove the load resistor from the circuit. Okay, we take it out. So I had a resistor connected here, I just took it out. Okay, that's step one. Step two is we're trying to find the Thevenin voltage, right? If we're trying to find the Thevenin, and it doesn't have to be in any particular order. That's why it says if trying to find the Thevenin voltage. So let's just say you're trying to find the Thevenin voltage. What you have to do is you have to use circuit methods. So basically stuff that we've already learned, KVL, KCL, parallel, parallel and series combinations. You could maybe have to use something more complicated like nodal analysis. Hopefully not. I don't know. It depends on what circuit you're looking at. But you need to determine VOC, which it's called the open circuit voltage. So I took my load out, and what I have is I have an open circuit here where I removed my load. This is called an open circuit, of course. It has no current flowing through it. It's just called an open circuit. So the voltage that I would measure there, if I solve this circuit, basically would be this node voltage, I'll call it VN1, minus this node voltage, I'll call it VN2. Typically that would be ground. So that would just be that I need to determine the voltage here. This would be 0, and I would know my open circuit voltage, which is my Thevenin voltage. Okay, and I wrote it here that the open circuit voltage is the voltage across the load terminals when the terminals are open. Okay, that's exactly what we're looking at there. So let's say I went and found my open circuit voltage. That is my Thevenin voltage. So if that was, say I went through and solved this all out and I found that this VOC was equal to 3 volts or something, then I would go right to my Thevenin equivalent, and this would be a 3-volt voltage source. Okay. Now, the second thing, if I'm trying to find, this is step 3, but it's the second of the 3 quantities we're interested in. If I'm trying to find Norton current, I use circuits methods, again, KVL, KCL, whatever, to determine the short circuit current, I short circuit. What is the short circuit current? It is the current through the load terminals when the terminals are shorted. So right now they're open when I want to find VOC. In order to find the short circuit current, I now short those terminals. So that voltage would be 0 now. But now I need to basically determine what is the current that flows here. And that is called my short circuit current. And that current is equal to my Norton current. Okay, so if I figured out that I went over here and solved for the current there and I got 2 milliamps for I short circuit, then that I would come right over here and my Norton current would be 2 milliamps. Basically this would become a 2 milliamp current source. Okay, so that's Thevenin voltage. Short circuit current is the Norton current, and the last thing is the Thevenin/Norton resistance, and that is the last step here. If I'm trying to find the Thevenin-Norton resistance, well, what do? I short all the voltage sources I have in my circuit. So I would go ahead and put a short right through this guy, or sometimes I'll draw it like this. You could remove the source and draw a physical short there. And then open all current sources. I don't have any current sources here, but if I did, I would open them. And then I find the equivalent resistance between the load terminals. Okay, so what the heck does that mean? Well, that basically means I am going to, let me remove some of this stuff. It'll be in the video, but I guess it won't be in the final slide because or I can just put it all back. If I'm looking for, so I shorted all my voltage sources, check. I opened all my current sources, I didn't have any, so that's a check. And I want to find the equivalent resistance between the load terminals, which are these two terminals here. What does that mean? Basically, it means I am going to send a little current in to this node. And that current's going to go through the circuit, and I want to know what is the resistance that that current has to go through in order to get back to this node. So that current's going to go into the circuit, and it's going to come back out of the circuit, and how much resistance is it going to see? So in this case, I would basically have, it would see this resistor for sure, and then I have a resistor to ground, right? This is a short. And then I have another resistor to ground, so it would see those two in parallel. It would never see this resistor because there's a short across it. So the equivalent resistance here is 0. So all the current that flows into this node will go this way. This is getting a little complicated, but just basically wanted to get you a feel for what the Thevenin resistance is. I'm telling you it is, if I have a current that flows into one of the terminals, it's also going to flow out of the other terminal, and I want to know how much resistance it has to see in order to get back to this node. Okay, that is what we're doing here. That is the explanation of the process of Thevenin and Norton. And then once I determine what that resistance is, so let's say I figured out that that resistance was 10K. That is now my Thevenin and my Norton resistance. So I would be completely done. I would have both equivalent circuits, and then I could throw my load resistor that I removed back out here, and I could measure the load current and the load voltage, and that would be the same as it would have been in the original circuit here if I had never done anything at all. Okay, that's Thevenin and Norton. That's the process. It is a lot. And in the next video, I'm going to go ahead and solve an example, or start solving an example. I'm sure it's going to be multiple parts, but try and just keep clarifying this and trying to hammer home some of the more important points by doing an example problem.